something sensitive like HDSDI video.
So where does that battle start?
It all starts and, frankly, ends with impedance. This cable is built to a broadcast standard of a very precise 75 ohms.
And holding that number steady over 300 meters is the real challenge.
That is the core engineering problem, yeah.
Okay, so let's unpack the anatomy then. What's fighting that challenge? The spec says it starts with an 18 AWG solid bare copper conductor. Now, a lot of cable is stranded because it's more flexible. Why insist on one single solid piece of copper here?
Well, it comes down to resistance, pure physics. Even before you worry about high-frequency signals, you're just fighting the physical resistance of the metal itself.
Just pushing power through it.
Exactly. That thick 18-gauge solid core minimizes that loss, so you're starting with the strongest, cleanest signal possible before frequency even becomes a factor.
And then wrapped around that core is something they call skin foam material. That's the insulation.
Yeah, and that's not just a spacer, it's what's known as the dielectric.
So its job is more than just protection.
Oh, absolutely. The exact thickness and, the consistency of that foam is what physically separates the conductor from the shield.
And that separation distance is what defines the impedance.
It's everything. If that spacing changes even a tiny bit, the signal starts to reflect back on itself and you get distortion.
Okay, so you have this perfectly spaced core, and now you have to protect it. And this cable has dual shield design? What? 2 layers?
Because you're fighting 2 totally different kinds of noise.
Okay.
So that first layer is a dual foil mylar screen. It actually gives you more than 100% coverage. That's really good at reflecting high-frequency noise. Think radio signals.
Sneaky stuff.
The sneaky stuff, right. Then the outer layer is a heavy aluminum wire braid. That's your brute force barrier. It handles lower-frequency electromagnetic interference.
Like when you have to run it next to a power cable.
Exactly. It's a targeted defense for environmental chaos.
This is where it gets really interesting for me. The attenuation table. This is basically the scorecard for signal loss.
Yeah, this tells the whole story.
At a low frequency, say 1 megahertz, the loss is tiny. It's less than half a decibel.
But nobody is sending HD video at 1 megahertz. You're pushing signals up in the gigahertz range.
Right. The spec sheet goes up to 3,000 megahertz.
Right.
And at that point, the loss jumps to almost 13 dB.
And that is a huge drop. That curve, how fast the power drains away as frequency goes up, is why this cable exists. It's engineered specifically to make that 13 dB loss over 300 meters survivable for the equipment on the other end.
So that battle against high-frequency loss is basically the whole point.
It is. It defines the performance.
We should probably also mention the velocity of propagation is 82%.
Which is quite good. It means the signal travels at 82% of the speed of light, which just speaks to the electrical efficiency of the design.
And from a practical side, it's got ratings like ULCL2.
Which just means you can safely install it inside walls in commercial buildings. The PVC jacket meets fire codes. It's about performance, but it's also about safety and compliance.
It all comes back to materials.
In the end, that's what super high resolution really means. It's material science being used to hold that 75 ohm impedance rock solid across an incredibly wide range of frequencies.
So here's a final thought then. If the entire performance depends on these tiny details, the purity of the copper, the exact thickness of that foam, and we know this cable has to comply with regulations like RoHS that restrict certain chemicals, it makes you wonder, right? How do those compliance decisions, which are about long-term safety and the environment, potentially affect the long-term integrity of the materials that are required to meet these extreme performance specs over decades of use?